All right, I think we can get started. So our first talk today is by Tachio Terauchi from Waseda University. Prior to being at Waseda, Tachio was also at JAST and before that at Nagoya and Tohoku University. Tachio works on techniques for building reliable computational systems and specifically has done work in a variety of different areas, including programming languages, program analysis and verification, but also synthesis, type systems, mathematical logic, automated deduction, and security. And he's going to be speaking today about constraint-based relational verification. We're very excited to hear his talk. Tachio, if you want to go ahead and share your screen, we're ready to go. Oh, you're muted.
Sorry.
There we go.
Hi, good evening. I'm Tachio. It's 11:15 p.m. here in Japan. I have a wife and two kids who are sleeping, so maybe I will have to be a little bit quiet. But I will give my best shot. Let's see. これでいけるかな? Wait, I don't think it's working. ちょっと待ってね. Please wait a moment.
I saw it for a moment.
これどういうふうにすればいいのかな。こうする。こうして、これでどうかな。あれ。
That's working.
Screen. Can you see a laser pointer?
Yes, but now it's in the presenter view. A moment ago, we could just see your slide.
How do I do this? 共有の、ちょっと待ってね。こうして、これでいいのかな? Let me do this. Okay. So here we go. Is this working now?
Yes, that's great.
Okay, good. The laser pointer working? Okay,
yes.
Good. So good evening. I'm Tachio. I will give a talk about constraint-based relational verification. This is a paper that appeared in CAB this year. This is a joint work with Hiroshi Uno, Lee of Tsukuba, and Eric Koskinen at Stevens. Okay, so this is automated verification. The topic of this talk is automated verification. Automated verification of relational properties, of course, because this is a workshop on hyperproperties. So we are interested in three classes of hyperproperties. One, K-safety, okay, which is a subclass of hypersafety. Prominent example of K-safety is TINI, termination insensitive non-interference, which is a two-safety property. This is a well-known security property that says that no information leaks, assuming that the only observable thing is the state after the termination of the program. Okay. Another class of hyperproperties that we are interested in this paper is co-termination. This is an example of a hyper-liveness property. So it falls outside of hypersafety. And roughly, co-termination is a termination property for multiple programs. It says that if one program terminates, then so does the other program. Okay. Another class of hyperproperties that we are interested in this paper is GNI, generalized non-interference, which is an example of a so-called for all exist hyperproperty, which actually is a subclass of hyperliveness. Roughly, so this class of properties of the form for all execution of some property, there exists a corresponding execution that satisfies a corresponding property. So it's a for all exists kind of relation property. So these are the three classes of properties that we are looking at, and we want to do automated verification for these properties. The main contributions of this paper are these three things. One, as it says in the title, we will do this verification. We will do the relational verification by reduction to constraints. We will reduce the relational verification problems soundly and completely to constraint solving. The key observation here is that relational verification amounts to synthesizing relational invariants and fair and semantic schedulers. And we will formalize this synthesis problem as a constraint solving problem. Okay. The remaining two contributions of this work is a new class of constraint that we call pfwCSP. I will let you know what they stand for later. And constraint solving method for this new class of constraints. All right. Okay. Having said that, go to the first main contribution. So the reduction of relational verification problem to constraint solving. I will do that. So to recap, these are three classes of hyperproperties we want to look at, we are looking at. And let's go with the first one, case safety. So a prominent example of case safety is TI&I, termination instance with no interference. And here's an example. This program, double square, takes a high security input H, a low security input X, and if H is true, then it sets Z to 2 times X. Otherwise, it sets Z to X. And afterwards, it iterates this loop Z many times. And therefore, if H is true, this loop will be executed 2X times, whereas if H was false, this loop will be executed X many times. At each iteration, Y is incremented by X. And after the loop exits, if H is false, you double Y and you return Y. So here's the question. Can an attacker who observes low security input X and return value Y tell anything about the high security input H? No. Okay, well, no, because I also say here that this computes 2 times X squared. And this, so looking at the output, you cannot tell anything about the high security input. The output is independent of high security input. This independence is exactly what non-interference characterizes. So formally, TI&I is a 2 safety property. It's a property about 2 execution phrases. And formally, so it is, if you execute this program double square with some high security input H1 and get output Y1, and you execute it again with some input H2, some high security input H2, and you get Y2, then these outputs Y1 and Y2 will be equivalent, provided that the low security inputs X1 and X2 are equivalent. So this is the typical termination instance that's non-interference. Okay, so here's a well-known way to verify TI&I. It's called self-composition. The idea here, the rough idea here is to find a safe relational invariant that relates the states of 2 copies of programs under a lockstep scheduling. So this is our program again. And let's say we run this under a lockstep scheduler. Say we pick as an initial state for the first copy, H is true. For the second copy, H is false, and X, the low input X, is 2. Okay. We execute this under lockstep scheduler. So each step we I realize that I cannot see clock, so I know what time it is. Okay. すみません。Where was I? Oh, yeah. Okay, so let's execute this on the lockstep scheduler. Now, in the first step, you go to L1, and this, as I just said, this doubles. You set Z to be 2 times X in the first copy, and you set Z to be X in the second copy, and therefore, in the first copy, Z is 4, and the second copy, Z is 2. You execute them again under lockstep scheduling, and this executes the loop, and the value of Y is incremented by X, so is incremented by 2 in this example run, and in both copies, and the value of Z is decremented in both copies. In the case of copy 1, it's decremented from 4 to 3. In the case of copy 2, it is decremented from 2 to 1. You execute these 2 copies again, one step in lockstep fashion. So both copies make a progress. And in the first copy, again, the value of Y is incremented by 2, and the value of Y in the second copy is also incremented by 2, and the value of Z is decremented by 1 in both copies. Now, at this point, copy 2's value of z is 0, and therefore it has finished executing the loop at L2. However, there are more steps that the copy 1 can take because its z is still 2, and we'll have to decrement it to 0 for the loop to stop. So the self-composition synchronization will try to synchronize the two copies. So we'll halt the execution of copy 2 at this point, and we'll only execute copy 1. What happens? So the copy 1 is executed, and the value of y is incremented by 2. The value of z is decremented by 1. The values of copy 2 do not move. It's still 2, 4. It still false 2, 4, 0. Execute the copy 1 again. Now the value of y in copy 1 is 8. The value of z is now 0 in copy 1. And so both copies, z's are 0, and they both exit the loop. And we are both copies at L3. Finally, since the value of h is false in copy 2, the value of y in copy 2 is doubled, and it will change from 4 to 8, and we are at the end of the program for both copies. Now note that the property we wanted to verify is satisfied in this example run, in that initially x are the same, and finally, y's are the same. So this was the property that we wanted. If the low security inputs are the same, so is the low security output at the end of the program. Now, the question is there, so this is an example run for the case the value of x was 2. Now, is there a simple relational invariant that one can find to prove that this holds for every execution, so every x? No. It turns out the safe relational invariant for this example is not expressible in linear integer arithmetic. This is proved in a paper by these guys. Okay, so this is a hard instance of TINI that cannot be proved by most existing method that like invariant senses, which are usually limited to linear invariants. So here's our approach to TINI. What we will do is we will find a semantic scheduler, SCH, and a safe relational invariant that holds under the scheduler. Okay, this semantic scheduler is roughly something that can allow us to choose which program to execute depending on the current states of the two programs. Right. Okay. So here is the same program, double square. Let's say we somehow found this scheduler, SCS, that says both copies move if the value of z in the first copy is 2 times the value of z in the second copy. And only the first copy moves if the value of z in the first copy is 2 times the value of z in the second copy plus 1. So roughly what this says is that every time the second copy makes a step, the first copy makes 2 steps. So here is an example run of the 2 copies under this scheduler. We start from the same state as in the previous slide. So initially the value of x is 2, and the first copy has h true, and the second copy has h false. So the initial steps is the same. The value of z is set to be 4 in the first copy, and the value of z is set to be 2 in the second copy. Note that at this point, the value of z in the first copy is 2 times the value of z in the second copy. And therefore, this case applies. Scheduler says both copies can move, should move. So both copies move, and the value of z is decremented in both copies from 4 to 3 in copy 1, from 2 to 1 in copy 2, and the value of y is incremented by 2 in both copies. Now, note that in this case, the value of z in the first copy is 2 times the value of z in the second copy plus 1. And therefore, this case applies. The scheduler says only the first copy move now. So the first copy moves, and now the value of z, only the value of y and z's in the first copy is changed, respectively from 3 to 2 and 2 to 4. At this point, again, this case applies because the value of z in the first copy is 2 times the value of z in the second copy. So both copies move, and we reach this state. And now this case applies, and so only the first copy moves, and the state becomes like this. And finally, both copies finished executing because the value of z are 0 in both copies. And we have this. Note that, again, the initial and the final state satisfies the pre and post that we wanted. Initially, the values of low security inputs are the same, and the value of low security outputs are the same. Additionally, if you look at the valuation of y's in these runs, you have this. So at every odd iteration of the loop, we have that value of y in the first copy is 2 times the value of y in the second copy, the value of y in the first copy, and the even iteration value of y in the first copy is 2 times the value of y in the second copy minus x. And these can be used to infer a safe relational invariant that proves the TI of this example. Yeah, it looks, this is abbreviated because the whole thing's quite large, but it's simple in that it is expressible in linear integer arithmetic. All right, okay. So now the question is, how do you express this as constraint solving? So the general flow of our approach as follows. We are given a program, or we are given tuple programs, because this is a relational property, tuple programs and a specification, and we generate constraint that is satisfiable if and only if the given verification instance is true. And at this talk, I will only explain this reduction from relational verification problems to constraint solving on specific concrete examples. Please look at the CHAP paper for how to do this in general for arbitrary programs and arbitrary specification of the respective class of hyperproperties. So in this example, we are given as a program this double square. And the specification is that if the precondition says if the value of x in both copies are same, and the post condition is the value of y in the same in 2 copies. And the constraint that is generated to encode the relational verification reasoning that I was going through in the previous slide is this. Okay. The key details are here. The I and the SCH1 and SCH2, SCH12, these colored guys are predicate variables. They are intuitively placeholders for concrete predicates. And the task of constraint solving, the goal of constraint solving is to find assignments, so, i.e. concrete predicates for these predicate variables that would make each of these clauses, each of these logic formulas logically valid. So this is called predicate. This is called predicate constraint. Prominent example of predicate constraint is constraint home clauses. This goes a bit beyond CHCs. We'll talk about that next. So roughly, these predicate variables I, this predicate variable I represents relational invariant that is preserved by semantic scheduler. These set of clauses, what they say is that relational invariant is inductive and implies Ti and I. Namely, this first clause says that is initiation. It says that invariant holds initially. So this is encodes the initial state of the 2 programs, and it says that the invariant holds initially. And this is a consecution step. It says that if the program makes a step from any state that satisfies the invariant, then the invariant remains to be satisfied. Finally, this is the finalization step. It says that if you are at the end of the program and the invariant is satisfied, then the post condition is satisfied. However, there is a caveat that is atypical of this. So that what I just said is the usual inductive invariant to prove safety or K-safety properties. The caveat is that we have this SCH. Okay, this represents a semantic scheduler. Roughly, SCH1 holds if first copy is scheduled to move. SCH2 holds if the second copy is scheduled to move. SCH12 holds if both copies are scheduled to move. So this clause that is in display says that if first copy is scheduled to move, then doing the move on the first copy from any state that satisfies the invariant, the post state remains to satisfy the invariant. And these clauses will be will be present for each scheduling. For SCH2, the second copy moves. SCH12, both copy moves. And the invariant has to be maintained for each of these possible executions. These set of clauses now says that the scheduler is fair, in that at least one unfinished copy must be scheduled if there is any unfinished copy. This is necessary for soundness because if we present an unfair scheduler, say this says that well only the first copy moves, then this would trivially satisfy safety because second copy never moves, and safety only says that if programs finish, then post condition, right? So a scheduler needs to be fair. If a program can move, it has to be eventually be scheduled to move, and these clauses ensure the fairness of scheduling. Note that for those of you who know constraint home clauses, this clause is not a constraint home clause because it has disjunctions at the head position. So these are predicate constraints like CHCs, constraint home clauses, but it cannot be expressed as CHCs. Okay. So that's K-safety. Now we will look at the next class of hyperproperties, co-termination. So as I said earlier, co-termination is termination property for multiple programs. Here we look at two programs, and we want to know whether these two programs, program 1 and program 2, agree on termination. That is, if program 1 terminates, then program 2 also terminates, and program 2 terminates then program 1 also terminates under a certain precondition. In this case, in this example, we choose as precondition, the value of their inputs are simply equal. Okay? X is the same as the other X, Y is the same as other Y. Now, do these programs satisfy co-termination? And yes. And formally, this property holds. Okay. That if you execute program 1 under some input, and it terminated and got output Z, output Z1, then program 2 does not diverge. It will terminate. Likewise, if program 2 terminates, then program 1 must terminate. So this is this expresses this co-termination property. Note that this is a conjunction of two asymmetric relational problem, which we call asymmetric co-termination. If program 1 terminates, then so must program 2. And other side says if program 2 terminates, then program 1 has to terminate. All right. So how do you? So we will reduce this co-termination verification problem to constraint solving. Here, before that, informal idea of this of what do we do. The idea is similar to what we did for K-safety. We will try to find a fair semantic scheduler and a relational invariant. In addition, we will try to look for a well-founded relation that holds under the scheduler. So here's the two programs again. And suppose we found a scheduler that says both programs move if the value of x's are positive in both programs, and only program 1 moves if the value of x in program 1 is positive, and the value of x in program 2 is not positive. So here is an example run of these two programs under the scheduler. Suppose we start with the value of x being 4 and the value of y being 1. So initially, the states of the two programs are this. Take one step. All right, and the values of x in both copies are positive. So both copies move, and state becomes this. And the value of x in both copies are positive, and so both copies move, and the values are changed as follows. Again, I'm sorry. And at this point, program 2 terminated, and also only the value of the first copy, only the value of x in the first copy is positive. So only the first copy moves, and the state changes as follows, and the state changes as follows, and both programs terminates. We can also find a well-founded relation that witnesses the termination of program 1 relative to the termination of program 2. That is, whenever after program 2 terminated, program 1 decreases its x and at each step, but x this value of x in program 1 is lower bounded by 0, and so it will program 1 will eventually terminate once program 2 has finished. And so this proves co-termination. Now, how do you do this by constraint? Oh, I'm sorry. And we can also find the relational invariant that shows that this is indeed proof of co-termination. Okay. So how do we reduce this to constraint solving? Again, the general idea is the same. We are given a program and specification. In the case of co-termination, these are two programs, and we want to verify that program 1, if program 1 terminates, then program 2 terminates under some precondition. And we output constraint. Again, this is in this talk, it's only for this concrete example, but to give you a taste of what happens in general case. The idea is similar to what we did for case safety. These i's represents relational invariant that holds is preserved under the semantic scheduler. Again, and the semantic scheduler is defined by this SCH1, SCH2, SCH12. Okay, these are also predicate variables. These are something that we also want to infer at the same time as we infer the relational invariance. Okay. In addition, we also have this predicate variable RWF. This represents a well-founded relation that we want to discover. That says that program 1 terminates, assuming that the program 2 terminated. So this initial set of constraints says that. So I is a safe inductive invariant, and RWF witnesses the termination of program 1 under the assumption that program 2 has terminated. And this set of clauses encodes that the scheduler is fair. This is similar to the fairness encoding for the case safety case, except that we additionally need this bound set by another predicate variable, f1. Okay, and this bound is used to bound the difference of steps taken in two programs to be only to be bounded. This is needed because, unlike in the case safety case, to express fairness in co-termination, we need to deal with a case that progressing but not terminating execution is forever scheduled. If we do that, then this other copy can get blocked forever because this guy keeps executing forever and ever and ever. And to prevent that unfair case, we will need this bounding. Okay. This ensures that the encoding is sound and complete. Okay, so that's it for the second class of hyperproperties. Finally, we will look at class of properties called GNI. So GNI is a security property for non-deterministic programs. Essentially, it says that if there is execution that exhibits certain output, then there exists a corresponding execution from a different type for any other high security inputs that could exhibit the same execution. So here's an example. So this GNI EX takes as an input high security input high and low security input low. And if high is true, it does this. If high is false, then it does this. If you look at this, both of these branches, what it does is if high is true, then it sets X to be a non-deterministic int. And if X is less than or equal to low, then it returns X. Otherwise, it loops forever. In the else branch, it sets X to be low, and it increments X some non-deterministic number of times and returns X. Now, is this secure? Can attacker infer the value of H by observing the low security input L and the return value X? No. It satisfies TIGNI, termination insensitive non-interference, which is formally hyperproperty of this form. So you execute GNI, this program, once under some high security input, and you get output X1. Then either executing the same program for some other high security input diverges, or there exists a terminating execution of this program, of this execution, which outputs the same output as this first execution. Okay. So this formalizes what I said informally about this security property. Also, it actually turns out to satisfy a stronger property called termination sensitive GNI, which says that if the first execution terminates and outputs X1, then the second there is a execution. Then the second execution can also terminate and output the same value. This is a so-called for exist hyperproperty because the first execution is the demonic or for all side. For all execution of this form, there exists the angelic side. There exists an execution of this form. So how do we verify GNI? Again, I will reduce the problem to constraint solving. And the idea here is to find, as before, find a fair semantic scheduler and a relational invariant and a well-founded relation, as in the previous two examples. In addition, we will also infer strategies for the non-deterministic choice side of the non-deterministic choices of the angelic side. The encoding for GNI, which I will not show in this talk because it's quite detailed, but it's an extension of the encodings for TI, NI, and co-termination that I displayed in this talk. The additional machinery that are needed are predicate variables that represent the strategies of the angelic side and prophecy variables that represent final outputs of the demonic side. This part is necessary for this encoding to be complete. I refer you to the CAB paper for details. Okay, so that's the reduction of relational verification problems with constraint solving. Now, what is this class of constraints that we propose that were used to reduce the problems to? Okay, so this is called pfwCSP. Let me go back. It's called pfwCSP. To describe this, I will first describe a pCSP, predicate constraint satisfaction problem. This generalizes a well-known CHCs, constraint Horn clauses, with non-Horn clauses. Formally, pCSP is a finite set of clauses of this form, where these x's are predicate variables, t's are a sequence of terms, and phi is a formula without predicate variables. Note that this is a generalization of a constraint Horn clause, namely, if the number of disjunctions here is less than or equal to 1, then this becomes constraint Horn clause. Now, this generalizes constraint Horn clauses to allow basically arbitrary clauses. And we say that the constraint pCSP C is satisfiable if there is an interpretation of the predicate variables that makes each of the clauses valid. Okay, so now having explained pCSP, I will now describe pfwCSP. pfwCSP is PCSP with functional and well-founded predicate variables. And it is actually simply, at least syntactically, is simply PCSP, but with predicate variable kinds. Each of the predicate variables in the clauses are classified into three kinds, either ordinary or functional or well-founded. And we say that set C of pfwCSP clauses is satisfiable if there is an interpretation that makes each of the clauses logically valid as before. In addition, we require that for each functional predicate variable, its interpretation is a total function. And for each of the well-founded predicate variable, we require that its interpretation is a well-founded relation. Okay, so that's it for the second contribution. It's actually quite a general extension of constraining home clauses, but it's powerful enough to encode all of the examples that we wanted to do, all of the classes of hyperproperties that we wanted to encode in this paper. Finally, I will present a solving method for this new class of constraints, pfwCSP. This solver combines the well-known CEGIS, CounterExample-Guided inductive synthesis approach with what we call stratified family of templates. So a recap of CounterExample-Guided inductive synthesis, CEGIS. Yeah. The idea here is to iteratively accumulate example instances E of the given clauses through two phases of these guys. Through these two guys. Okay. The first phase is synthesis phase by a learner. Here, the learner tries to find a candidate solution role that satisfies the example instances. The second phase is the validation phase by a teacher. In this phase, a teacher tries to check if the candidate solution that is proposed by a learner is actually an actual solution, a genuine solution. And if it's not an actual solution, it infers new example instances that witnesses that disproves that candidate is an actual solution. And this iteration repeats. The validation phase proposes new examples. The synthesis phase will propose new candidate, and see this iteration goes on until hopefully converges. So here is an example run of CEGIS. Suppose we are given these three clauses, okay, as constraints, and we initially start our run with an empty set of examples. And suppose the learner proposed this as a candidate solution. Okay, maps the predicate variable I to be true. Now, is this an actual solution? The teacher says, well, let me look at it, and we'll try to check if each of the three clauses are logically valid under this interpretation. And it turns out, no, it's not an actual solution. Namely, the third clause is not valid when x is 0. So this third clause under the assumption that x is 0 is added as a new example. Simplified is simply saying that I cannot be true as 0. And learner using this example will infer a new candidate that works at least for a current set of examples. And the teacher says, now, is this a new candidate, this guy, that maps I to x less than 0? Is this an actual solution? The teacher says, no, you're still wrong. Okay. Why? Because the first of these three clauses is now violated. And this is given as a new example. Simplified says that I has to be true at 1. Oh, by the way, so in this talk, I say, so some work on CEGIS classifies examples into positive examples, negative examples, implication examples. Here, we call all of them examples, okay? Positive, negative, or implication, or there's generalization of it. Yeah. Now, having these two examples, the learner proposes a new candidate solution. Is this a genuine solution? Teacher says, no, you're still wrong. The second clause is not validated. So a new example is proposed. So this is a generalization of implication example. Now, a new candidate solution is proposed by Lana. Is this a genuine solution? And finally, teacher says, yes, that's true. And CEGIS stops. This is how CEGIS works. In Lana, we use a template-based approach. In this approach, we prepare a solution template that contains unknown coefficients, and we generate constraints on them and solve them using an SMT solver. For example, say these are example instances, and this is a solution template. From this example and a template, we will generate constraints on the coefficients, unknown coefficients C1 and C2, and we'll run SMT solver. That gives us a satisfying assignment, and from it we can infer a candidate solution. This is actually not our invention. It's actually quite often used in the ICE work. Okay? So this is template-based learner. In addition to this, we have our extension, which we call stratified template families. So in a prior work by some of us, we have proposed this stratified template family for CEGIS-based invariant synthesis. This was to achieve completeness often, but at the price of efficiency. The rough idea here, the rough idea of the stratified template family is to have strata of templates of increasing expressibility, and each strata is a finitary template, but you can there are infinite levels of stratum. And the idea is to search for solutions in a stratified manner. Iteratively, you start from an inexpressive template and you gradually move to more expressive ones as needed. In our pfwCSP solver, we adapt the stratified template families, but we extend it so that it is adapted to CEGIS instead of CEGIS. And also, we use it to infer all three kinds of predicates in pfwCSP: ordinary, functional, and well-founded. This is to achieve not only completeness, but also efficiency. By that, so CEGIS is data-driven, whatever that means. So you have these example instances that are sort of like points in the space, and you try to fit the solution over these points. And there's a well-known problem called overfitting that if the solution space is too expressive, then you overfit. And this stratified template family has a nice effect of avoiding overfitting. Okay. We have implemented the solver in a tool called PCSAT, and we tested this on 20 relational verification problems. Some of them are K-safety properties that are taken from prior work. Some of these are co-termination problems. Some of these are GNI problems. And we were able to, our tool was able to verify 15 of these 20 problems fully automatically. 5 of these required some manual hints. Okay, so I will conclude my talk. So in summary, we have proposed a new class of predicate constraints called pfwCSP, which generalizes the well-known CHCs with non-horn clauses and functional and well-founded predicates. And we have shown a sound and complete reduction of various relational verification problems, K-safety, co-termination, and GNI, to solving pfwCSP. The key idea here is that, key observation here is that relational verification amounts to synthesizing relational invariance that relates the states of multiple program executions, and a fair and semantic scheduler that executes these multiple copies of program in a fair manner, and in a manner where a simple relational invariant can be found. And the idea is that this can be characterized by our new class of constraints, pfwCSP. Finally, we have proposed a stratified CounterExample-Guided inductive synthesis for solving pfwCSP constraints. The idea here is to combine the classic Armando 2006 CEGIS with this idea of stratified family of templates for achieving completeness and efficiency. Finally, there is an implementation of PCSAT that you can try. It's available from here. So that is it. Thank you for listening.
Thanks very much, Tachio, for a very interesting talk. We'll just have a few minutes of questions and then let you go. Thanks for joining so late. While folks are thinking about questions, please, everyone, feel free to add them in the Q&A button. But while people are thinking, I have a question. On the part of your work where you talked about the co-termination analysis, you said you needed to give a bound on the unfairness, basically, at each state, like how many times one of the programs could run while the other was paused, if I understood correctly. It seems to me like it could be, in some examples, there might not be any finite bound that would work for that. Like it could be that you would need somehow one program needs to run arbitrarily long compared to the other one. But you mentioned it sounded incomplete. Could you give some intuition for why that's the case?
Sure, that's a very nice question. It's good that I get to ask these very technical questions. Somehow it was justifying this is putting technical details in the slides. Okay, so co-termination. So here's co-termination problem. We want to verify these two programs co-terminate. Okay. And this was our encoding. And the bound, let me do away with these dialog boxes, is this. Okay? This gives a bound B, and this says that the difference between the two executions Z has to be within the bound. Okay, so you're asking, why is this complete? Can you always find a bound? So note that this bound can depend on the state. So this happens at the initiation phase. So it says that initially you pick a bound based on the input values of the program.
Okay.
This is a predicate. This is a functional predicate variable. Any interpretation of this has to be a total function from input to output. So I'm looking at the predicate. Well, I'm cheating and looking at the relation as a function. This is input and output. And so it says that you can pick this bound based on the input.
Okay.
It's not a fixed bound for the programs, but it's a bound that can depend on the input.
Okay, that makes sense. Thanks. I think Boris had a question.
Hi, Tachio. Thank you for the talk. It was really interesting. Are the examples available somewhere? So the examples that you discussed about co-safety, TINI, non-inference. So we believe our model checker should be able to verify those, and we would really like to try them.
Yes, please try. So I, at least at the time of writing, I don't, the only existing work that could verify some of these examples was this paper by that I mentioned.
I checked out your CAV21 paper. I see that there is a evaluation section, but the examples are not in the paper. So
okay. So I'll do that. So only existing work, as far as we knew at the time of the writing, was this paper in CAV19 that proposed that was titled property directed self-composition. And they actually proposed this double square example, which is a very nice, by the way. It's very nice work, their paper. And they were the only ones to verify the case safety examples of our paper. We basically took all of the case safety examples from their paper. But their tool was not, their method was not fully automated. They required the user to provide atomic predicates that can be used as invariants. In our work, it's completely automated. Now, it would be nice for if you had a new way to solve these instances. The examples, the actual concrete examples are in the longer technical report that is available in our web pages, in our home pages. And most likely it is also available in the, in the GitHub. 画面の共有。In the this GitHub link.
All right.
Right.
Thank you very much. We'll be most likely in touch with you.
All right. Thanks again, Tachio. I think in the interest of time, we'll keep moving here. So